Okay, today's lab is about friction. Alright, so the first measurement is the empty friction cart and the pass car. This is the pass car. It's got a little spring gun on it, some notches at different levels of compression for the spring. You hit the little button, and it's a little spring gun. It shoots the car off, and it's got magnets on the end of it and Velcro on the other end of it, so you can do collision experiments with them, and a nice tray up top so you can put bar weights on top of it. Anyhow, we're going to use the red pass car here, so I'm just going to put it on the scale and you can write down the mass. There we go, 257.4. Alright, now that's in grams, so I believe, of course, if you do most of the calculations, many of the calculations, you may need newtons, and you have to convert that to kilograms, so watch out for that. Now, here is the friction cart. You got three different choices. A plastic cart, that means the bottom of it, where the friction surface is, either plastic or felt or cork. And I've found that it's easiest to work with the plastic. It has the least amount of friction and works the best, or has given me the best results, and it's the easiest to time and everything because it slides for the longest with the least amount of friction. So let's get the mass of this one at 92.0 grams. Now that has three significant figures, and notice that I write the 0 down to indicate definitively what the third significant figure is. Alright, now three significant figures is enough. Even if it says in here to the nearest 0.05 grams, we're just going to the nearest tenth of a gram. That's good enough for us. Alright. Okay, the next part is to get the distance that the pass car may push the friction cart. It says to get the distance from the wall to the far edge of the friction cart. Oh, this is the initial position, so this is the starting point. And it's with the spring gun fully deployed. So, you know, it's going to shoot the car, and as soon as the spring gun is fully deployed, then the spring force is no longer acting on the car, and we want to measure it from that instant on. And so it's fully deployed, it's up against the wall here. Oh, but I'm skipping that a bit. Before we do that, you see there's a problem here. The cart is not stable. It's not staying in one position. It starts to accelerate to my left, meaning the table here is not level. And so we don't want that to affect the results by putting an extra force of gravity acting on the cart. And so I have some scratch paper here I'm going to put under this edge over here to try to level it out so it doesn't have a tendency to roll due to gravity. I'm just going to fold these in half one time, see how much it's going to take to level it out. I'm not sure. It's just trial and error here. Not enough. Gonna have to get more paper. Okay, I got more paper then. Ooh, that's close. It's just moving a little bit. All right, it is now level. No tendency to roll that way. No tendency to roll either which way. You can give it a little push, and it'll go a little bit, and then it'll stop due to friction. And nothing else in either direction. Okay, that seems to be good enough. Uh-oh. Oh, okay, good. Now, back to the distance measuring. So, I have put it on this end with the fully deployed spring gun. Then we put the friction cart. So the friction cart has a hook here, and it just hooks right down onto the pass car like that. So the pass car can push the friction cart. And now, again, I say again, one thing, of course, to keep in mind throughout this experiment is that we are going to assume that the axle on the wheels, or the wheels, don't have any frictional effect that is going to be measurable or considerable compared to the friction cart. So any friction due to the wheels, we're going to pretend or ignore it or assume that it's not enough to be considerable error. And let me show you these wheels, how well they turn. They turn super good, watch. So very little concern about friction in the wheels causing a notable error. But, you know, some wheels have a little bit more friction than other ones. Like this one right here seems to not spin quite as freely as the other ones. So there is some error in this assumption, but compared to the friction of the cart, we're going to assume it's negligible. Okay, anyways, on to the distance measurement here. So we're measuring from the wall to the end of the cart. That's going to be our initial starting position. Well, we can get 3 significant figures here. Okay, so I'm not going to tell you what I'm measuring. I'm going to show you, and you're going to measure it yourself. Alright, so here it is. Let's see if you can get that measurement right to the edge of the cart. The front edge of the frictional cart. I'm getting it. Make sure this ruler is pushed against it. So right to this edge right here. It's going to be really close to 36. Make sure everything's level here. We don't want parallax errors. I can see I could move back and forth for parallax errors. But we don't want that. So anyways, I'm getting about 36 point something. You guys can decide exactly what you want that third decimal, or the decimal place to be for that third significant figure. Okay. Okay, now we need to do the test fire. Make sure this frictional cart doesn't just fall off the edge of the track. That would not allow us to measure a distance if it went all the way off the edge. So, it says to test fire on the third level end. That's basically the strongest plunging level, I believe. So I'll try it on this one. And it says to use the edge of a ruler as a convenient way to start it. Now the problem is if you push that button with your finger, you know, friction on the button in your finger will put a little pulling motion and throw off the consistency of your shots. But the smooth edge of or smooth side of a ruler, you just push that button and it'll have negligible friction, and it will also be very consistent with it because it's just a smooth side of a ruler rather than the soft fingertip. So here we go. I'm going to try it for the first test. Oh, it went all the way off the edge. And in that case, instead of going to the third notch, we're just going to go to the second notch and test fire it with the second notch. All right, take 2. Definitely didn't go off the edge. What's going to be difficult about that, though, is timing it, because it's going to be a very short time. Let's try the third notch one more time, and it'll be the same. Well, it didn't go all the way off the edge that time, but it definitely went off the edge. So second notch is what we seem to have to use here. One more test fire. Okay, this is going to be a challenge to measure the time, but I got my handy stopwatch, and I will try to do like I did in the last video and say go when I push the button, and stop when I stop the button, and you guys can try to time some of them at home for the fun of it. All right? Heck, I might even make you time all of them on the video or from the video, just like I did last time, right? Right. Okay, well, let's do the first time here. One. That's the second notch. Okay, on your marks, get set, go. Man, that was only 1.03 seconds. That's what I got from that first time here. Oh my goodness. Let's see here a second time. There we go. And the second time. Ready, set, go. Man, this is going to be a little more fluctuating time. 1.10 seconds that time. Oh, I was forgetting to measure the distance. So we have to scratch the first time and redo that one because I forgot to measure the distance. I'm supposed to measure the distance from the starting point, which we just measured, to the ending point. How far did it push the cart? So let's get that measurement here on this second trial. Actually, no, more like 76.1. 76.1 centimeters. So it went from 36.1 to 76.1. Okay, so that's the basic idea. We got to do this. It says at least 9 good times in a row. All right, fun. All my data, distances that I measured, and each corresponding time above it. Of course, all your data should be shifted over to the left one column. I just messed up there and I didn't start back over on the left. I wanted to point out one data here. One time is one of the shortest times, 1.19, and also corresponds to the longest distance that I measured, 80.8 centimeters. And I might mark over here, these are all in centimeters, so I'll put centimeters here. And then that's an outlier, I believe, but I didn't discard it. I wanted to point that one out, and because of that one, I decided to do an extra trial over here, 131, and it came out to be 80.4. So you see the time is much longer, or notably longer compared to 119, and the distance is a little bit shorter, so that's why this one is short time and the longest distance. That doesn't correspond to the expectation, so it might be an outlier. You might could just throw that one out or keep it in the average and hope the averaging out will take care of it. But whatever, you need to calculate the average distance and subtract it from the initial distance that we measured at the beginning and get that for your delta D right there. And of course, calculate your average time as well. All right, the timed trials are done. The next thing is a set of calculations to make a prediction. I'm going to leave you guys to do the calculation because, well, I'm going to do it myself and I'm going to make a prediction. So that's the point of them, is to be able to make this prediction all the way down here. First of all, of course, to calculate the coefficient of kinetic friction, which is a constant for this plastic track and the plastic bottom of the friction cart here. That's assuming, you know, that the force of kinetic friction between the two is constant across the whole surface of the track. And then we can say what force of friction there will be present in the track when I put one of these 250-gram bars inside of the cart. So now it has more friction on the cart, and the goal is to be able to predict how much force will it take to pull this cart and the car with this 250-gram bar. All right, I wanted to explain a little bit more about what's going on here with this experiment. So when the pass car is pushing this friction cart, of course there's a constant, well, that's our underlying assumption, is there's a constant frictional force slowing the car down and making it stop. Of course, Newton's law of motion says that in the absence of an external force, an object in motion will remain or stay in motion, or an object at rest will stay at rest in the absence of an external force. So the instant that this spring gun finishes pushing, or it gives it its initial speed, there's no other force except for friction acting on the car and the cart. And we are assuming that the friction acting on the cart is the principal source by far that is stopping everything, and we are timing it. Now, by timing it and measuring the distance, we get the kinematic equations of motion come into play, in which we can figure out what the deceleration of this system is. Now, it's just referred to as A experiment, or AEXP, in the calculations here, but that's the experimental acceleration, which is actually a deceleration that is causing this system to stop. If we know what the deceleration is, and we assume that it's constant throughout the experimental time, then you can simply multiply by the mass of the system and you have a force. And that would be, of course, the force of kinetic friction that is causing the system to stop. Well, if you know the force of kinetic friction, of course, the force of kinetic friction is in the opposite direction of motion. So it's this way for the friction. And if you know what that value is, then you can use the definition of friction and solve for what's known as the coefficient of kinetic friction. The definition of friction is just simply the normal force acting on the object times a constant, and that constant is known as the coefficient of kinetic friction. The normal force acting on the object, in this case, of course, it's the cart, the friction cart. The normal force is calculated simply as the reaction force due to the cart's weight pushing down on the track. And so the track pushes up on the cart. That's Newton's law of motion, right? For every action, there is an equal but opposite reaction force. Okay, so the normal force is pushing up on the cart. If you know what the magnitude of it is, you just simply take that and multiply it times a constant, and you have the frictional force. Now, think about this. We're taking a force, which is called the normal force, and multiplying it times a constant to get another force, called the frictional force. Well, if you take force times something equals force, guess what? That something, that constant, can't have any units. It's the coefficient of kinetic friction. It is a unitless number, but it is taken as a constant as long as the surface is the same, or the two surfaces rubbing together. As long as the two surfaces rubbing together are the same, then you say that they're going to have this frictional coefficient, which takes the normal force, converts it to the frictional force. So that's what we're doing in these calculations. Once you have, well, maybe I should write it on the board. All right, so very basic here. I'm going to draw the frictional cart, and just a rectangle, and of course the track that it's on. And so the normal force is straight up, and you can say that's the normal force, okay? And it's acting on the bottom of the cart. Now, let me do this in free body diagram form. That means that you just take and make an outline of the object, and you put all the forces as if they're starting at the center of mass of the object. And then it's convenient because they're all having this same origin. So a free body diagram should have the normal force starting at the center of mass of the object. And you say, okay, fine. That's the normal force, and I know it's actually acting on the bottom of the cart, but I'm going to put it at the center of mass to give all the force vectors a common origin. And then you say, well, then the weight is acting downwards for the cart, so you can put it like that. And then if the cart is being pulled along this direction, or pushed along this direction, then it will have speed or acceleration. So I'll just give it a speed vector, okay? And that speed vector is going to be changing. So I'm not putting it at the origin because it's not a force acting on the cart. It's just a speed vector, a velocity vector going to my left or right, whichever way you're looking at it. Okay, so what is acting, another force that is acting on the cart, of course, is the friction. And the friction, of course, is acting down here again. And you say that's the force of friction. I think I have it in the lab sheets. I have it as a lowercase f with a little k on it for frictional force or kinetic friction, right? And that's acting to the right. Now, you can see why this is slowing it down because it has a speed to my left. The frictional force is acting to the right, and that's causing it to decelerate. It constantly slows down. Well, we measured that deceleration through kinematics. We just measured the distance and the time, and then use simple kinematics to figure out what that deceleration was. And so you have the acceleration AXP that we get from the calculations, and then you just multiply it times the mass of everything, the m total, right? And that is also friction, right? Because the only thing that's causing that experimental deceleration is friction. And it is slowing everything down, including the pass car, which I'm not drawing here, but it slows the pass car down and the frictional cart down. Everything slows down at once. Then that's all caused by friction. Hope you can see that okay up there in the picture. Anyways, so what is the other definition of the frictional force? Well, that's what I was talking about a minute ago. It is just a constant, mu k, Greek letter mu, a little k to indicate kinetic friction, times the normal force, right? And that gives you the same result. So we have two equations for the friction. This one and this one, right? And so that's why we end up with the last equation to calculate mu k. So we can set this one equal to fk also, all right? And then well, what we want to do is solve for the coefficient of kinetic friction. So mu k is going to be equal to the frictional force, fk, divided by the normal force. Which I think in the lab sheets, the normal force is actually indicated as a big capital F with a subscript N. So big capital F with a subscript N. So it's the normal force right here. So I guess we should put that up here in the diagram as well. This is a big capital F with a little subscript N. You know, the symbol is arbitrary as long as you know what it is and you indicate that accordingly in your writing. So that gives us a way to solve for the frictional force. The coefficient of friction. We know the normal force. We can calculate that. That's very simple. The normal force is just defined as the mass of the object, and this is going to be the mass of the cart, times the acceleration due to gravity, g. And so that's very easy. We measure the mass of the cart. We know what the acceleration due to gravity, the constant, 9.8 meters per second squared. And so we can plug that in, and we have the bottom normal force and the top frictional force. We know the frictional force from the kinematic results up there. So we have everything that we need to calculate in UK. Now the next part of the lab is going to be using the UK to make a prediction. What we're going to do is, instead of just having the mass of the cart, we are going to have mass of the cart plus a 250 gram bar mass inside of the cart. Okay? And that would give us a bigger normal force because it's still the same equation, mass times the acceleration due to gravity, but the mass is bigger, so the normal force will be bigger, and as a result, the frictional force will be bigger. Okay? And we can predict what that frictional force is because we know what mu k is from the first part that we just finished. All right, so then if we know what the frictional force is, we're going to make a prediction that, hey, if I'm going to attach a string and pull the cart, then this is going to be a tension force, a big capital T, or you could put F with a little subscript T. A tension force is going to be pulling the cart to the left, and it has to be strong enough to overcome the force due to the friction with the extra 250 gram bar in the cart. And so T, in order to overcome the friction, has to be equal to Fk. And if it is equal to Fk, then we'll be able to just barely start the cart, and it will slide down the track, pulling the pass car at a constant rate because the forces in both directions are equal. So if it starts a little bit moving to the left, it'll just move at the same rate nonstop because all the other forces are balanced out. And there'll be a net zero force, but if we start it moving, it'll keep moving. That's, again, Newton's law of motion. Now, the tension is going to be due to a hanging mass. So it's just going to be, in this context with the extra mass in there, we call this the Fk predict, because it's the predicted frictional force based on what we found earlier. And then it's going to be equal to hanging mass, I call m hang, times the acceleration due to gravity. And so all we need to do then is predict the hanging mass. That we're going to need is, of course, just Fk predict divided by the acceleration due to gravity. And so that's just coming from this equation to get this. And so we can predict how much hanging mass will be required to overcome the friction. I thought to add this in just so you're not confused. This Fk right here is indeed still the same, of course, as Fk predict. There's only one frictional force that we are talking about, kinetic frictional force. And it's, if we add in the 250 gram bar, then we are then going to be claiming to predict this one right here as well. So it's going to be Fk predict on that one. So at any given time, there's only one kinetic frictional force. And these are identical. One kinetic frictional force, and we predicted what it is based on knowing what the frictional constant, the coefficient of kinetic friction. Make our prediction, in addition to the mass of the cart, which we measured earlier, we need to get the precise mass of this 250 gram bar right here. So 250, when it's written like that, you don't know how precise it is. It could be 250 plus or minus 1 gram, which is kind of what this implies at minimum for the precision, but it could be 250.0 plus or minus a tenth of a gram, or it could be 250 plus or minus a few grams. It's not specified, and significant figures are very important, and so we have to check them when they're not specified very concretely. And so here we go. Look at that. See, it was just 250 grams plus or minus a few, and in this case plus 4.1 grams, so it's 254.1 grams, and that makes a difference in the third significant figure, which it's always good to be precise, at least at 3 significant figures whenever possible. Alright, so write that mass down for the precise mass of the bar. Now the cart mass was 92 grams, so you could just write it up here, just for convenient reference, 92.0 grams for the mass of the cart, plus the bar mass we just measured, 254.1. That'll give you M total, which we use in the calculation here. Now I'm going to go through and do all of these calculations to get my prediction for the hanging mass. I'm not going to tell you what I get. Hopefully you guys can get the same value, and we're going to put it to the test. No friction in this pulley right here. That is not a source of appreciable error. There's not enough friction to worry about. Alright, so I got my prediction. I put this 250 gram bar inside the friction cart. I have an increased amount of friction caused by the cart, heavier cart on the track. And of course kinetic friction resists the direction of motion, which is going to be down the track from the tension from this hanging mass. So I got my total mass. Now I need to take into account the mass of the hanger plus any other masses that I add to the hanger right here. And we'll see if that works. Let me get the mass of the hanger real quick. Which you guys should find. How much am I adding to this hanger right here? Let me see if it works. I need one of these, one of these, one of these, one of these. Oops. One of these ones. So it should be precise enough. Okay, let's see if that gives me total amount, close to the total amount that I need. That's pretty close to the total amount I need. So here it goes, the big test. Add them onto the mass hanger and see what happens. Alright, when I release it, ideally the cart will just barely start to move and barely slide down the track. Whoa, that wasn't barely. That wasn't barely. That was pretty fast sliding down the track, huh? Well, that wasn't super fast. And it starts all on its own. Ideally, it'd be slower than that. So let me try taking off this little half-gram mass and see how much of a difference that makes. Look at that. That's pretty good right there. Ooh, it slows down. Has a little bit more friction, not constant. That's pretty good right there. That's pretty good. Right? Alright, so I'm actually going to put, for the qualitative result on that prediction of mine, and assuming that yours will come out to be the same mass, because you use the same numbers, I'm going to actually put it as okay. The next part of the lab is the surface area and kinetic friction. So I'll ask you this question. What do you think if I put the block, this is my wooden block, if I put it on its side like this, will it have more or less friction or the same than if I put it flat like this? That's the idea of surface area and kinetic friction. Doesn't matter, as long as the surfaces are the same, you know, this side of the block is the same as this side of the block, and of course the surface of the track stays the same. So is it going to be more friction flat or on its side? Or will it be less friction? Or will it stay the same? That's the question that we're going to put to the test here. And so all we have to do in order to put it to the test is put the spring gun in. I'm putting it all the way into the third notch, putting it against the wall, and I want you guys to honestly write down on your sheet here whether or not you think it'll be different, and if you think it'll be different, do you think it'll be more or the less friction when it's flat compared to when it's on its side? Okay, so write that down, like right up here at the top. Say, I think the block will have the same friction on its side as when it's flat, or I think the block will have more friction when it's flat compared to when it's on its side. And more friction, of course, would mean that it'll stop the car faster, and less friction means that it'll take longer to stop the car. So let's start out with it flat. Okay, now to me, I don't know, I would initially think, okay, that's more contact with the surfaces, you know, more contact between the surfaces, and that's going to cause it to be a greater friction, right, and stop the car faster. So let's see how far the car travels when it's flat. Okay. Well, it doesn't matter too much in terms of how far it travels. We just need to know its final position. So I'm going to put its final position when it's laying flat as 71.2 centimeters. That's after the first try. Let's do a second trial here. Trial number 5. That one went a little extra far. 75.0 centimeters. Okay, so that was 5 trials on the flat side. Okay, now on the side, the same spring launch level, and trial number 1 here. Now again, I predicted, at least if my uneducated prediction, I would have thought the flat side would have had more friction and stopped the car faster. 67.3. 7.3. Well, those on average, I can tell just from looking at them, did come out to be a little bit shorter, it looks like. I could do a couple more trials just for the heck of it. Interesting enough, this is not the ideal result. This is not the ideal result. And then the question where real science begins is why? Why is this not the ideal result? So, this is not the ideal result because the ideal result, as it says in number 5 right here, is that they will be the same. The surface area of contact does not influence the amount of friction. Because as we showed on the board, friction is only the normal force times the coefficient of kinetic friction. There's nothing about surface area in that. The normal force is just dependent on the weight of the object. And if it's sitting on a flat surface, it's just the weight of the object. And it doesn't matter whether you put it this way, or this way. That's the theory, is that it will be the same friction. In fact, I could try it this way, just for the heck of it. See what that does. Now, what could be causing it to not be ideal is the interesting question. And this one went much less distance. Okay. So why did this one go much less distance? So there's my distance data for the two different positions of the block. Alright then, finally, last part of the lab is static friction. And in the interest of time and convenience, because I don't have someone to help me conveniently measure the angle of the track when I lift up one end of it for this part of the procedure, I'm not going to do this part, and you guys get to omit it from this lab. So omit that part. But I will just say a couple of words about it. And that is that static friction in general is expected to be greater than kinetic friction. It's harder to start the object moving than it is to keep it moving if it's just sliding on the surface. Okay, that's the basic idea. The idea was just pretty simple to calculate the coefficient of static friction. We can figure out what the force is that's parallel to the ramp whenever we lift it up. So if I have this and I lift it up to a certain height until it just starts to slide. Oh, see right there, it started to slide. Oh, and so I would just find that point of where it barely starts sliding. And somewhere right around there, okay? And then someone would measure the angle that this track is making with the level surface. Okay? And so then we could calculate, the weight of it. So I have this 250-gram bar in there. Or I could take it out and you calculate the weight of the the cart, the friction cart, with or without the bar. And then we could say what component of it is coming down the ramp. And then we say, well, static friction builds up and builds up and builds up until it can't stop the cart's weight from pushing it down the track anymore. So at that point, we know that the static friction is basically equal to the component of the cart's weight that is coming down the track. So we can figure out what it is if we could measure that angle precisely and exactly have it at the point where the cart just starts to slide. It seems to be right about this height. You see, if I go a little bit higher, it's sliding. Go a little bit lower, it's not sliding. Okay, so if I go higher, there it's starting. Lower, it's not. Now, the second idea that was interesting in this part that we're skipping is that it's this angle at which it slides versus not sliding. That angle at which it just starts is independent of the mass. So I could put the 250-gram bar in there, and the angle still stays the same, at which it just barely starts to slide. Okay, that's the ideal again. So now it's sliding, now it's not sliding. So somewhere in between those two right there. And ideally that's independent of whether or not it has a 250-gram bar in there. Not sliding, not sliding. Okay, that's the basic idea, and the reason for that is that, if you have a bigger mass in there, the normal force on the track, or from the track, increases, causing static friction to be greater, and of course the component of the weight going down the track is also bigger, but it has to overcome a greater static friction, and so as you add more mass, those two increase directly proportional to each other. The component down the track increases at the same amount the normal force increases, so that the static friction is enough to compensate for the extra weight going down the track, and they balance each other, and the angle stays the same at which it will start to slide. That's the ideal. Alrighty then. Well, that's all we got for this video, though. So good luck with all those calculations, and see you in the next one. Error.